Okay, yes, so thank you for the introduction. My name is Monika. I'm a PhD student at the TU Florian, and today I want to talk about large-scale generalized additive models and how we can estimate them probably efficiently in a Hessian-free way. So we're jumping more back to the topics from yesterday, not about GAM and VEC models anymore, but it's also a bit about eigenvalues and matrices. So first of all, in a generalized additive model, or in short GAM, I assume that my response is from a distribution in the exponential family, and then I allow for a transformation of its mean and model this transformed mean as a sum of the constant of some smooth terms. Well, those smooth terms we have here, and again, we usually assume that they are built as a linear combination of some basis functions, and then I will evaluate those basis functions in my covariates. I obtain a fixed model matrix, and my GAM simply turns in a generalized linear model, which is now over-parameterized due to the spaces expansion. And therefore, I will estimate it with a penalty, a quadratic penalty, and this penalty should ensure me that my smooth terms are indeed smooth in the end. So I'm in the standard penalized log likelihood estimation for the generalized linear model, and I will obtain my better parameters by this iteratively reweighted penalized least square optimization. So I solve for the betters by linearizing the model to the Taylor approximation, and then solving the penalized linear model in each step. And what can be viewed like special in the GAM case is that we also estimate the smoothing parameters. We have one smoothing parameter, lambda, for each smooth term f here. And that can be done by different approaches. Some are prediction error based, but mostly it's done by putting a Bayesian view on smoothing and estimating the smoothing parameters via the marginal likelihood. And if I do a performance iterated approach, I will only consider the marginal likelihood in the iterative weighted linear model, and then it takes this form. So we simply have the linear likelihood with the penalty part and some log determinants, where this is the log determinant in the Hessian. Okay, and this will become the thing we are most interested in during this talk. Well, in nowadays settings, we are more and more interested in estimating GAMs in the case where we have a large number of observations combined with a large number of parameters. So those n and p dimensions become large. And then in the classical estimation, first of all, of course, storing the model matrix X can become expensive, but most importantly, forming the Hessian or the expected Hessian will take me n times p squared computation operations, and in each iteration of the PCG-Hutchinson I will need to solve with the K matrix for the beta parameters. So I need some kind of Cholesky decomposition of the K, and this is cubic in the number of parameters in terms of complexity. And additionally, for the REML updates, I have those log determinants in K, which can become numerically unstable if some of the smoothing parameters go to infinity while others remain small. And that is totally plausible if I have many different smoothing parameters. Okay, and there are different, mostly two strategies to handle those large-scale GAMs in the literatures. And one strategy is to exploit sparsity and to decompose the K by using specific sparse structures in this matrix. And the other approach, which is more related to the classical GAM literature, is to discretize the model matrix and to use a parallel pivoted Cholesky decomposition for the matrix K. Well, but both of those approaches still rely on explicitly forming the matrix K and factorizing it. And this is, of course, still the bottleneck if I'm in a dense setting. And now the question is, instead of trying to accelerate this bottleneck by using parallelization or some sparsity assumptions, can we bypass it entirely? And there's some literature on deep learning and also on Gaussian processes where they do Hessian-free optimization. And Hessian-free optimization in the deep learning context is built on the idea that I use some approximation of the Hessian and then incorporate the second order information via this approximation in the optimization of the model parameters by solving with a preconditioned conjugate gradient with this approximate Hessian. And what they do for large Gaussian processes is not only using like conjugate gradient for solving for the model parameters, but specifically to use Hutchinson trace estimation for the derivatives that come up in the marginal likelihood. And we want to do this as well, but combine it with a closed form update formula for the smoothing parameters, the Fellner-Schall scheme, which is also only derivative based. Okay, and this is supposed to be termed Hessian-free because we never need to form K. We only need matrix or matrix vector products with K. And we totally avoid this unstable log determinant and the marginal likelihood by simply only looking at the derivative of the marginal likelihood. Okay, I only want to say a few words about trace estimators. So for any quadratic matrix A, if I have a random vector set with an outer product that has the expectation being the identity matrix, I can use the simple trace expectation trick here, and this will be true. And then I can form a Monte Carlo estimator of the trace of A, where this average here. And what you should note is that I only need to form matrix vector products with the matrix A for this. And then there are some results that if I use specific distributions of this vector set, specifically that each entry has the same probability of being -1 or 1, both being 1/2, then I can obtain some very good relative error measures for this trace estimator. Okay, I also only want to say a few words about conjugate gradient algorithms. So with the conjugate gradient algorithm, I want to solve this system of linear equations where my K is assumed or needs to be a symmetric positive definite matrix. And I do this by minimizing this quadratic function instead. And specifically, this algorithm adapts the gradient descent algorithm, so to say, by changing the search directions such that in each step they are mutually K conjugate, so that their inner product defined by K results in 0, and this will iteratively give me a basis. I form my solution as a linear combination of this iteratively built-up basis. Somehow by adapting the search direction, it becomes a bit more efficient. And also, what is important to note, even though I don't show you this explicit algorithm, it only needs matrix vector products with the matrix K again. And yeah, the convergence of the conjugate gradient depends on the ratio of the largest to the smallest eigenvalue. That is also called the condition number. And if this is smaller, I will obtain a better rate of decrease in the error rate of this algorithm. And that's why we use preconditioned conjugate gradient when it's mostly applied. That is, one multiplies the system with a matrix M, which is a cheap approximation to K and easy to invert, and hopefully reduces the condition number of the system. Okay, now in the generalized Fellner-Schall scheme, in this performance iterated update of the smoothing parameters, so where we only look at the linearized working model, each smoothing parameters can be updated by this formula here, which is built by setting together the derivative terms and the Riemann criterion in a way that it will ensure me under step size control and step towards minimization of the Riemann criterion. Okay, and the log determinant and its derivative becomes this trace, which is now the most computationally demanding part for the smoothing parameter estimation. And as I've said, we don't only want to solve in each IRLS step for the smoothing parameters. We also, for the beta parameters, we also want to estimate the trace and then update the smoothing parameters by this way. And to make this work, we want to use a conjugate gradient solve where we have several right-hand sides. And the first right-hand side is for the approximation to the beta estimate in each step. And the other right-hand sides are vectors of Rademacher samples. And then I know that those other approximate solves for the system are approximately K inverse times this matrix set. And then I obtain my trace estimator by multiplying and averaging for each solve obtained here, transposed times SJ times ZR. Okay, a lot of formulas right now. The question is, does this indeed become or can become faster than the exact solve? Of course, it's only approximate, and now can it become exact? Can it become faster by only being approximate? And the answer is that the number of parameters definitely has to be large. So for exact solve, I need to form the matrix K and do some Cholesky decomposition. And for the Hutchinson trace estimation, together with this block conjugate gradient, I need to iteratively form new multiplications with the matrix K. Multiplication with the matrix K, I firstly need to multiply with the penalty matrix and then with X, so this has this complexity. Then I have to do this for each right-hand side and for each iteration of the conjugate gradient. Okay, so therefore, if the number of Hutchinson samples times the iteration of the conjugate gradient definitely remains smaller than the number of parameters, it will be faster. Okay, and what is also nice to note is that this conjugate gradient procedure can simply exploit sparsity if I have it in the matrix X and the penalty matrix, and doesn't require some specific structure like a banded structure like the Cholesky decomposition, since it doesn't care about controlling the fill-in. Okay, yeah, I can, of course, implement it in an efficient way by implementing this multiplications in a parallel way, where I will not do all the multiplications for all rows at once, but I use blocks of rows and blocks on the right-hand side, or the entire right-hand side. Okay, and I never need to store the full X matrix, of course, as well. Now, let's look at some simple simulation results first. Here we have sampled 1,000 observations, assuming that our response follows simple smooth term, like this one here. And yeah, we've sampled Gaussian observations around this and modeled the smooth terms in a GAM by some p-splines with 250 parameters. And yeah, the nice thing is that it definitely returns the same smoothing parameter as the exact solve. The fifths also look quite similar, and the beta parameters with the conjugate gradient also are similar mostly, and the trace estimate, like after very few updates of the Fellner-Schall, like stays unchanged. Okay, and then a little bit of a more complicated examples. Here we have simulated 2,000 observations, assuming that our eta is now the sum of 3 different smooth terms. And we've simulated response data from 5 different distributions in the exponential formula: Gaussian, Poisson, binomial, gamma, negative binomial. And yeah, as basis representations in the GAM model, I now chose cubic p-splines, cubic regression splines, and thin plate regression splines, and each had 500 basis functions or vectors. And yeah, the penalty matrix then is the sum with the blocks of zeros in there. And yeah, the approximation looks good. On the first side, we can see here the approximation for each type of spline on a log lambda grid from 1 to 10, and for each distribution, like, not the approximation, but we can see the true estimate of the trace versus the conjugate gradient plus Hutchinson estimation. And what is, of course, also interesting to see, that it indeed can be faster than the MTCV implementation, even though the MTCV implementation is implemented in C++. But of course, for this, I have to scale up the number of parameters. For a simple GAM, it will definitely not be faster. Okay, then taking a closer look at this trace approximation, we see that it looks good for the p-splines and the cubic regression splines, but it doesn't look so good for the thin plate regression splines for all distributions. And well, this is simply due to the fact that thin plate regression splines definitely have a worse condition number by the way they are constructed than cubic or p-splines. And as I said, this will lead to a slower convergence of the PCG, which I cut off at 1 point, and therefore to a worse estimation of the trace. Okay, And then the thing is, or the question is, like I also already looked only at simple preconditioners. So all of the results previously were formed with a simple diagonal preconditioner. And then I tried to test if it does get better for the thin plate regression spline if I use like a block diagonal preconditioner, where I have the diagonal for the simple X transposed X terms, and I use block inverse for the S terms. That actually doesn't help much. We see that the error rates for the thin plate haven't improved much. And yeah, so the question is if like I really want to continue looking at thin plate regression splines, because from construction perspective, they might not be the best or first choice in a large scale setting anyway, because the way they are built, they are quite complex to build and already requires some kind of eigenvalue and eigenvector decomposition of the matrix with the basis functions. I think I will rather continue looking at the P-splines, but then as well, I need to definitely take a closer look how I can find a well preconditioner, because once I get more smooths in there, definitely the conditioning can or will become worse. And I want this preconditioner not only to fulfill the standard criteria, like being efficiently to invert, but I also don't want to form the model matrix K. For example, standard preconditioners would use incomplete Cholesky factorization, but then again, I would need to form the matrix K. Okay. And apart from this, there are also definitely more efficient Hutchinson-type estimators, like the Hutchinson++ estimator, where like this also depends on the spectrum of the matrix, so how the largest eigenvalues look like, and I do a different computation for the largest eigenvalues. But this is right now cannot be combined with this way, again, of not forming the matrix K. So the question is there a way to work around this? Okay, so thank you for your attention, and if there are any questions, I'm happy to answer them.